Hello students, as we discussed chemical properties of haloalkanes in some previous videos, now let us discuss chemical properties of haloarenes. In this video, we are going to focus on the nucleophilic substitution reaction, and the further type of chemical reaction will be discussed in the next video. The reactions of haloarenes are classified into three types, that is nucleophilic substitution reaction, electrophilic substitution reaction, and reaction with metals. So, in this video, we are going to discuss on nucleophilic substitution reaction of haloarenes. Do you remember what is nucleophilic substitution reaction? Nucleophile is electron-rich species which get substituted. The halide part get removed and in the place of that OH group comes. OH group, we can say X is removed, OH is get substituted. So in the case of haloalkane, we discuss this reaction. Here OH negative is the nucleophile, and similarly we have discussed the different examples while taking different nucleophiles we have discussed in the case of haloalkane. Now let us discuss the same reaction for nucleophilic substitution reaction for haloarenes. That means here we are writing haloarenes by AR. X, it is haloarene. AR here represent a benzene ring here. So it is different from this. This here R is the alkyl group, but here AR is the represent the aryl. That means the benzene ring. So benzene ring, instead of writing I'm benzene ring, I'm writing AR here. R. AR X. That is haloarene. Now same reaction, that is a nucleophilic substitution reaction. When it takes place, so here the X will get removed and OH will take this position. So we get a AROH. When you write the product, it is very easily you can write the product. That means you need to remove the X and you have to keep OH. OH is the nucleophile here in the place of X. So the X will get removed as one of the side product here. Now let us discuss this equation. That is this equation in detail. When you compare the reactivity of alkyl halides and aryl halides, this is also called as haloalkanes. This is also called as haloarenes. So whenever I am using a word haloalkane, that relates to haloalkane relates to alkyl halide. Haloarenes relate to aryl halides. So when you compare the reactivity of nucleophilic substitution reaction, it is found that alkyl halides are more reactive than aryl halides. So we can say that the aryl halides show less reactivity towards nucleophilic substitution reaction when it is compared with alkyl halide. So first we want to discuss the reasons why the reactivity is lesser for the case of aryl halides. So let us discuss the reasons for it. First reason, that is resonance effect. Resonance, it is one of the most important concept in organic. As I told you during the vacation time, practice all the resonating structures. So we are applying the resonating structures now while dealing with different concepts in the organic. So resonance effect, when we make the resonating structure for chlorobenzene, that is this one. So we'll get the resonating structures like this. So this is the resonating structures which we have already discussed in +1 class. So make the resonating structures for this. Now, due to resonance, you can find that there is a partial double bond between the Cl and the carbon. You can see here Cl and the carbon on which the Cl is bonded, that carbon have a partial double bond. So because of the resonance, there is a partial double bond between the CX bond. So as we know that greater the number of bonds, difficult to break. That is, when the bond order increases, the cleavage is difficult. And when it is difficult, then the substitution takes place very difficultly. That means it is less reactive towards the nucleophilic substitution reaction. So, in short, what we can say that due to resonance, there is a partial double bond character between the CCl bond. Therefore, greater the number of bond, it is difficult to break. Therefore, it is less reactive towards nucleophilic substitution reaction. So, when the question is asked in the exam, no need to write to explain the answer. You need to make just a resonating structure and this point which is underlined here. So, no need of explanation, just write it to this one, that due to partial double bond character, that is due to resonance. You need to make the structure also and this point also whenever it is asked in the exam. That is always 1 mark question. So no need to explain the answer, but keep it this for your reference. Next point, that is difference in hybridization of carbon atom in CX bond. Now, when you compare an alkyl halide and aryl halide, in alkyl halide, this carbon atom is sp3 hybridized carbon, as we have discussed already, and this carbon atom in the aryl halide is sp2 hybridized carbon. Because of the sp2 hybridization, when you compare sp2 with sp3, in sp2, S character is greater. So because of this, it can hold an electron pair of CX bond more tightly than sp3 carbon. So in the case of this one, it will hold the CX bond more tightly. Because of this reason, what happened? The bond length get lowered. Bond length gets shorter. So when the bond length gets shorter, we can say that it is difficult to break. Therefore, it is less reactive towards nucleophilic substitution reaction. So this is for explanation, but when the question is asked in the exam, you need to only draw the 2 structures which is shown here. These 2 structures you have to draw, and you have to represent the sp2 sp3 carbon here, and you need to just write this point which is given here, the underlined point. The sp2 hybridized carbon have greater S character, therefore bond length is shorter and thus less reactive than the haloalkanes towards nucleophilic substitution reaction. So in your notebook also, you will be only going to write the point which I have underlined here. So no need to elaborate, and because the same content is given in the textbook, for your reference you can take the text also, but in the notebook write it the underlined point only. Next is instability of phenyl cation. So before explaining about phenyl cation, in the case of haloalkane, which is represented by Rx, there is a cleavage of CX bond which results in the formation of R plus and X minus, where R plus is called as carbocation, and we have discussed that 3 degree carbocation is more stable than 2 degree than 1 degree. So greater the stability of carbocation, there will be ease of the reaction. That means the reaction takes place easily. The same case when we consider here also, we found that here also, in order to do a nucleophilic substitution reaction, there is a cleavage of this bond. This is cleavage of CX bond and with the removal of X negative, there is a formation of positive charge here, that is called as phenyl cation. As in the case of haloalkane, carbocations are formed, but here in this case phenyl cations are formed. So because this phenyl cation is actually unstable one, so because of this reason of instability of phenyl cation, this reaction will not take place easily. We can say that in case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance. So here this phenyl cation, it will not be stabilized by resonance, therefore it is unstable. So that is the reason of less reactivity of nucleophilic substitution reaction. So for the exam purpose, only you need to write the point here. The point is instability of phenyl cation. So you need to write only this point, instability of phenyl cation. Let us discuss replacement by hydroxyl group. Let us take one example, that is chlorobenzene. Chlorobenzene is one of the example of haloarene. Here there is a formation of product, that is phenol. So let us discuss this equation. In this equation, on heating the aryl halide with aqueous NaOH solution at 623 Kelvin and under 300 atm pressure, and on acidification, it gives rise to phenol. The formation of phenol takes place here. Actually, this reaction takes place in two steps. That is, the first step is this step. That means it is treated with aqueous NaOH at 623 Kelvin and 300 atm pressure. At the time, there is a formation of a product. That is, the product is, this is called as sodium phenoxide. First, there is a formation of sodium phenoxide. Then later on, with the acidification, that is acidification, second process, it gives rise to phenol. So in the first process, that is the first process, when you give the condition NaOH 623 Kelvin 300 atm pressure, it gives rise to sodium phenoxide. Sodium Na is sodium, O phenoxide, phenyl group and one oxygen, sodium phenoxide. And when it is treated, or we can say when it is acidified means H plus ion, it gives rise to phenol. So here there is a formation of phenol. So in short, we can write the reaction directly in this way. Let us discuss effect of electron withdrawing group in a nucleophilic substitution reaction, that is a replacement of X by OH negative ion in haloarenes. That is, in this reaction, let us see how the nucleophilic substitution reaction get affected when there is a electron withdrawing group. The presence of electron withdrawing group NO2 at ortho and para position increases the reactivity of haloarenes. Look at the three equation which is given here. In the first equation, this equation is taking place at 443 Kelvin. And because here there is a presence of one nitro group at the para position, this is the para position. So we can say that the reaction, that means the substitution, is taking place at lower temperature than the first without a nitro group. So in the next case, you can find that here there is two nitro groups. That means this nitro group, and these nitro group, one is at ortho position, the other one is at para position. So because of the presence of two nitro group, we can say that substitution, that is removal of Cl by OH, takes place at the temperature 368 Kelvin. That means lower than the first value. Now substitute 3 nitro groups, that is at ortho position, para position, and this is also ortho position. So when we substitute 3 nitro group, at the time just on warming we can get this product. So that means which product takes place easily? That is this product. This reaction is taking place very easily, just we need to warm this, we will get the product. But the other two, you can say the first one require the temperature, that is 443 Kelvin temperatures required. The second 368 Kelvin is required, and here just you need to warm it, then you will get the product. So why it happens? In all these substitution is taking place, that means removal of Cl and substitution of OH is taking place. But in all these reaction, we can say that the reaction will become more easier when there is a substitute, that is nitro group. Nitro group is an electron withdrawing group. So the presence of electron withdrawing group, it make the reaction more easier. So how this nitro group at ortho and para position increases the reactivity of haloarenes towards nucleophilic substitution reaction, that we need to discuss through a mechanism. Its mechanism can be explained by making the resonating structure for haloarene for the substituent group at ortho position, nitro position and meta position. Let us make this structure separately in order to understand more clearly. This is equation which is given in the textbook. You can note it down from the text. When the nitro group is present at para position, the resonating structure will be in this way. You can see NO2 nitro group is at a para position when the substitution takes place. So it undergoes the resonating structure. These are the resonating structure. So in this case, what it is observed that the nitro group which is at para position withdraws the electron density from the benzene ring, thus facilitate the attack of nucleophile on haloarenes. So by the resonance it facilitates the attack of nucleophile, hence the reactivity increases because of the presence of nitro group at para position. Similarly, if the nitro group is at ortho position, you can check here, this is the nitro group which is at ortho position. Here is the ortho position. Nitro group is at ortho position. At the time also it undergoes a resonating structures. You can find here there are resonating structures. These are the resonating structure. And because of the presence of nitro group at ortho position, it withdraws the electron density from the benzene ring. So because of this reason, it facilitates the attack of nucleophile on haloarene. Because you can find in this step there is the resonating structures, it is drawn, and because of the resonance there will be a ease of nucleophilic substitution on haloarenes. But when the nitro group is present at meta position, at the time it undergoes resonance, but in this case, since the nitro group is not at ortho and para, it is at meta position, here it will not withdraw the electron density from the benzene ring. So thus we can say that the presence of nitro group at ortho and para position withdraws the electron density from the benzene ring, and thus it facilitates the attack of nucleophile on haloarenes. And this is due to the stabilization through resonance. So resonating structures are more important here. You need to write the resonating structure of each in your notebook. Since this structure is taken from the textbook, so you can note it down from as it is from the textbook. So in this video, we discussed about nucleophilic substitution reaction of haloarenes, in which we have found it out that haloarenes are less reactive than the haloalkanes because of the reason that is resonance effect, difference in the hybridization of carbon atom in CX bond, instabilities of phenyl cation. And when it is observed that the presence of electron withdrawing group at ortho and para position will increases the reactivity of haloarenes, and its mechanism is explained, that is mechanism is explained due to resonating structures. So this is all about the nucleophilic substitution reaction in haloarenes. The next properties, that is a chemical property of haloarenes, will be discussed in the next video. Thank you everyone.